Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about how to find the radius and interval of convergence of a power series. Okay, so in our last video we looked at finding the center of a power series. We also looked at a little bit about what the radius of convergence will do to determine the convergence of a power series. But now we're actually going to go take a series and physically find its radius and what we call the interval of convergence of that series. All right, so let's get started. So again, a power series is a series in the form the sum of a sub n times x minus c to the n power. And again, it's a series written as a function of x where c is the center. So here are two important definitions. The radius of convergence we looked at in the last video. The radius of convergence is the distance from the center that a given series converges. Okay? And now we have the interval of convergence, which is the set of all values x for which a series will converge. Okay? It's all the values that the series will converge for. All right? Okay, so let's take a look at how we find those two things. To determine at what value or values a power series will converge, again, we're looking for the values of x that power series will converge. We're going to use the ratio test. All right, back from the last half of this chapter, one of our series tests, that's an important one, that ratio test. Okay, so here we go. Let's find the radius and interval of convergence of this power series. We're going to do it with the ratio test. So the ratio test says I take the limit as n approaches infinity of a sub n plus 1 over a sub n. Notice that it's a sub n plus 1 and a sub n, not x. So when I replace my n plus 1s in, they're going in for n's, not for x's. So that stays x plus 2 to the n plus 1 over n becomes n plus 1. 4 to the n becomes 4 to the n plus 1. All right, times, okay, remember a sub n goes on the bottom, so it gets flipped up. So it's n times 4 to the n over x plus 2 to the n. All right, so far so good. So now let's try to clean this up. Let's take the limit as n goes to infinity. Again, let's try to see if we can do this quickly. So we have x plus 2 to the n plus 1 over x plus 2 to the n. So this term has one more x plus 2 than this one does. So that would leave me with an x plus 2 in the numerator. That one more. That takes care of those two. We have a 4 to the n and a 4 to the n plus 1 in the denominator. So that means this one on the bottom has one more power of 4. So there's going to be 1 power of 4 on the bottom. And then we have an n over n plus 1 still. That has to be worked out with the limit as n goes to infinity. But the limit as n goes to infinity of n over n plus 1 will be 1, right? So that leaves me with, after I calculate that limit, the absolute value of x plus 2 over 4. But again, I'm trying to use the ratio test to determine, right, the radius and interval of convergence to figure out where this converges. So the question is, what does the ratio test tell us about convergence? Well, the ratio test says that if the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, it means the series converges. So then I would need this, the absolute value of x plus 2 over 4, to be less than 1 to make this thing converge. Okay, now I'm going to try to solve for x. That's what I'm trying to do. I'm trying to get x alone. I want to solve this thing for x. So that means the absolute value of x plus 2 has to be less than 4, right? If I multiply by 4 on both sides. So now it's an absolute value equation. So it becomes x plus 2 has to be less than 4 and greater than negative 4, right? This absolute value inequality. And I'm going to subtract 2 from everybody. I get negative 6 is less than x is less than 2. Okay. Now, I've learned a couple of things, important things from this inequality that I have. I know the radius of convergence, R is 4. So this series converges 4 units from its center. Remember, its center is -2, right? It's x plus 2, so the center is -2. So it converges 4 units away from that center. And then I have this inequality at the bottom. -6 is less than x is less than 2. My interval of convergence I'm going to write -6, 2. I'm writing it as an interval. Let me erase this because I'm going to need a little more room here. Fill one more thing in. Okay, so that's my interval of convergence. I know I is -6 to 2. All right, so within that range. So basically what I'm saying to you is, hey, if I were to graph this on a number line from -6 over to 2, I know that this series will converge for any value of x between those two. But the question is, does it converge at -6 and at 2 at the endpoint? Well, I don't know, because the problem is, if you take a look, what happens? If you were to take 2 and substitute it in for x, let's say back up, or let's say back over here. If I were to take 2 and substitute it in for x, I get 2 plus 2. 2 plus 2 is 4. 4 divided by 4 is 1. But remember, for this thing to converge, I need the absolute value to be less than 1. Here I get an answer that for the limit that's equal to 1. And what do I know about the ratio test? When the limit is equal to 1, the test fails. So I have to use another test. So I have to check the endpoints. I'm going to check each endpoint in the original series that I see up top. So I'm going to start with 2. I'm going to start at x equals 2. Substitute that one in first. It's a little easier to work with. It's the sum of 2 plus 2 to the n over n times 4 to the n. That's the sum of 4 to the n over n times 4 to the n. The 4 to the n's drop out. It gives me the sum of 1 over n. Well, what do I know about this series? Oh, this is the harmonic series. It's divergent. So at x equals 2, this thing diverges. It gets a parenthesis. We're determining parenthesis or bracket. Does it count or not? So that would be an open circle on your number line, right? Now at -6, let's see if I can fit it in here. When x is -6, if I substitute that in, I'm going to drop the sum sign in a minute. -6 plus 2 to the n over n times 4 to the n is going to be -4 to the n over n times 4 to the n. That's -1 to the n times 4 to the n over n times 4 to the n. Those drop out. Now I get -1 to the n over n. Well, what do I know about -1 to the n over n? Let's come over here. -1 to the n over n. That's an alternating series. So the question is, does this converge with the alternating series? Well, the alternating series test says the limit as n goes to infinity of a sub n has to be 0. Well, it is, right? You have 1. Remember, you ignore the alternating part. And then a sub n plus 1 has to be less than or equal to a sub n. The next term has to be less than or equal to the one before it. So that would be 1 over n plus 1 has to be less than or equal to 1 over n. Yeah, that's certainly true. So then this converges by the alternating series test. So the -6 counts and gets a bracket. It's like getting a closed circle there. And that's the radius and interval of convergence. So to find the radius and interval of convergence, you're going to use the ratio test. Okay, the ratio test, just like you normally would, you knock out anything that has an n in it, you're left with an absolute value inequality that has x in it. And you need to know when that absolute value is going to be less than 1, because the ratio test says that's when the thing converges. And then you're going to solve that absolute value inequality. Okay? Solve that absolute value of inequality. It gives you the interval of convergence, but then you have to test the endpoints, because there's no guarantees that the endpoints make it converge, because the endpoints, when you substitute them in, it's giving you 1, and the ratio test fails at 1. All right? That's how this whole thing works. All right, we're going to try a couple more. Let's try to find the radius and interval of convergence for this power series. Same concept. So we're going to use the ratio test. Take the limit as n approaches infinity, 2 to the n plus 1, x minus 2 to the n plus 1, over, it's going to be n plus 1 plus 2. That's going to be n plus 3 factorial times, flip this thing over, right? It's supposed to be divided by this whole thing, so we flip it over. N plus 2 factorial, 2 to the n, x minus 2 to the n. So again, we're trying to clean this up as best we can. Let's see, 2 to the n plus 1 over 2 to the n. There's one more power of 2 up there than in the denominator, so there's a 2 up on top. X minus 2 to the n plus 1 over x minus 2 to the n. There's one power left of x minus 2 that's there. This is n plus 2 factorial over n plus 3 factorial. There's one more power of there's an n plus 3 down on the bottom, right? There's one more term on the bottom than there is up top. So there's going to be an n plus 3 left on the bottom. Now, what's the limit as n goes to infinity? The limit as n goes to infinity of this, well, that's 2 times x minus 2 over something really, really big. That's really, really small. That goes to 0. But 0 is a value that's always less than 1. Right? I need to know when this limit is less than 1. Well, 0 is always less than 1. So what does that mean for me? Well, if 0 is always less than 1, that means this thing will converge for all values of x. There's no x to solve for in that absolute value inequality. So it converges for all values of x. So how do we write that? So the radius of convergence will be infinity. Okay? The radius of convergence is infinity, and the interval of convergence is negative infinity to positive infinity. It's all real values, all real numbers. All right? We don't need to solve that absolute value inequality like we did on the last slide. Okay? All right, let's try one more. We're going to try the sum n equals 0 to infinity, n factorial, 2x plus 1 to the n, over square root n. So again, same thing. We're going to find the limit as n goes to infinity. Let's do it. That's n plus 1 factorial, 2x plus 1 to the n plus 1, over square root n plus 1, times, flip the other one over, square root n factorial, 2x plus 1 to the n. Okay, let's try to clean it up. N plus 1 factorial over n factorial. This one contains an n plus 1 that the other one does not. So we're going to write that. Get rid of those two. 2x plus 1 to the n plus 1 over 2x plus 1 to the n. It's going to give me a 2x plus 1. And this is square root n over square root n plus 1. I can't really clean that up, so I'm just going to kind of leave it there for now. Now, I want to know when this limit is less than 1. Well, here's the thing, though. If I were to multiply this square root n by this term here, it gives me an n to the 3 halves. That's going to be greater than the n to the 1 half that's in the denominator. So now if I take the limit as n goes to infinity, the dominant power is in the numerator. It's n to the 3 halves over n to the 1 half. Since the dominant power is in the numerator, this limit approaches infinity. And infinity is certainly not less than 1. So what does that mean? Well, that means this thing won't converge at all. Or will it? So the first thing it means is that the radius of convergence is 0, right? So x dropped out. I can't solve the inequality. So the radius of convergence is 0. The question is, what is the interval of convergence? Well, you might say, well, there is no interval of convergence. It doesn't converge. But it does converge. It converges one time at one place. This thing will converge at the center. Remember, any power series will converge at the center, no matter what. So the center, 2x plus 1, if I just take 2x plus 1, set it equal to 0 and solve, I get negative 1/2. So the interval of convergence is only negative 1/2. And again, it has to converge at the center. If I take negative 1/2 and substitute it in here, I get 0 to the n. But that's 0. And then 0 times all of this stuff will be 0. And the sum of 0 is 0. So it has to converge at least the center, no matter what. All right, so the radius is equal to 0. Okay, it doesn't converge beyond the center. The interval of convergence, though, is all the values it converges for, and that is only the center, negative 1/2. And that's it. Those are the three cases that can happen when you're finding the radius and interval of convergence of a power series. The first one here, this one is the most likely one that you'll get. Okay, these are kind of special cases, but it's good to see them as well. Again, this is the most common case where you're going to have to do all the work. All right, then solve the inequality, then test the endpoints. There's a lot to do. Okay, and that's it. As always, thanks for clicking.